So I want to talk about the composition of blood first. So when we take a vial of blood, we can spin it in a centrifuge really fast, and this is what we get. So we have this bottom portion, and we're going to call this bottom portion our hematocrit, or hematocrit. So hematocrit is just blood cells, essentially. And this is going to make up about 40 to 45% of our blood. Here we're going to have the buffy coat, which this makes up our white blood cells. And then here we're going to have our plasma. And in our plasma, we are going to see things like albumin, we're going to see globulins, and we're going to see fibrinogen. Cool. Now that you're an expert on blood, let's go to poop. Red blood cell breakdown. Does make poop though. So first things first, we start with heme. I'm actually going to erase this so it's out of the way. Okay, so let's say you have your blood, right? And I don't know, you get bruised or you have a cut or, well, not a cut. Don't say cut. It's bad. Your blood cell gets tired and needs to be recycled. So first thing that's going to happen is your heme is going to be returned to heme, or via heme oxygenate, is going to be turned to a variation called biliverdin. Biliverdin is then going to be turned to bilirubin via bilirubin reductase. Now bilirubin is water insoluble, so it actually can't sit inside your blood. But we have albumin, that blood protein we talked about earlier that I just erased. Albumin is going to carry bilirubin through the blood vessels until it gets to the liver. At the liver, once the bilirubin gets inside the liver, it's actually going to undergo a process called conjugation, where bilirubin gets gluconic acid attached to it, and then they together are going to go outside the liver via a bile duct and into the intestines. Now, in the intestines, we have hungry bacteria. These bacteria love carbohydrates, and they're going to eat the gluconic acid, chomp it right up. In this process, somewhere in the intestine, our bilirubin is going to be converted to a chemical called urobilinogen. So urobilinogen has two possible pathways it can go through. It can either go through the blood vessel pathway and go to the kidneys, or be excreted and then it actually does some of this again, but ultimately it's going to end up at the kidneys. The kidneys, inside the kidneys, the urobilinogen is going to become urobilin, and that's going to be excreted as pee. Or urobilinogen could become strechobilin, which is poop. Three things we're going to be talking about. First, not vasoconstriction. It was vasoconstriction. My bad. Vasoconstriction, platelet aggregation, and coagulation. All three simple, not so simple steps we're going to talk about. So, first things first, let's start with vasoconstriction. Yeah, we'll start there. That makes sense. So this is a blood vessel. It could be anywhere in your whole body, but let's say you get a break in your blood vessel. So first thing that's going to happen is the pain response or the pain reflex, which is the thing that happens when you feel pain, actually causes the cells around here to constrict to hopefully alleviate some of the blood flow and also help our later platelet coagulation or platelet aggregation and coagulation to occur. We'll talk about that, but the point being is they contract to make the wound smaller, if it's possible. So, on to platelet aggregation. This is a process, but we're going to get through it. So, I have two things written here. I have a VHF, which is this factor. I always forget how to say it. Von Willebrand factor. I guess it's VWF now I think about it. It's VWF. So, we have the Von Willebrand factor, and we have this platelet, and I have IN for inactive, and off of that we have a receptor for the Von Willebrand factor, VWF. So, even though this has a receptor for von Willebrand factor, this guy can pop on and pop off this receptor all day long and nothing's going to happen. It only happens when this guy gets tugged on and becomes activated. How does it get tugged on, you may ask? Good question. So, this von Willebrand factor, he is extremely attracted to negative charges. Just so happens that we have a basal membrane outside all our capillaries, and they are naturally negatively charged. So this von Willebrand factor, he's going to come up here. I'm going to denote him like this as a little line. And then our inactivated platelet is going to come and attach via its receptor for the von Willebrand factor. And that, as the blood is flowing, is actually going to cause that tugging motion. This inactivated platelet is now going to transform, grow, swell, do a whole bunch of stuff. And I'm greatly exaggerating what this looks like, but he's going to become ginormous, something like that. So this platelet is going to have three types of things it releases. The first thing, well, not the first, but one of the three things that releases is something called alpha granules. This platelet now becomes a granulocyte, and it has these granules that's going to start pumping out into the environment. The alpha granules include, break that. Alpha granules include more von Willebrand factor. They also include, they include platelet-derived growth factor, and they also include, let's check my notes real fast, fibrinogen. I don't want to get it wrong. Fibrinogen. Okay, so these two are going to go on to activate more, or help to activate more platelets. Von Willebrand factor is going to go attached. Platelet-derived growth factor helps these platelets grow. Fibrinogen, we'll come back to that in a second. We're also going to have dense granules. Dense granules. So dense granules are going to be ADP. We're going to have calcium, and we're going to have serotonin. So ADP and calcium specifically are going to go on to attach to activate more of these inactivated platelets, so that way they can become active even without binding to anything. And then they're going to go on and attach at another receptor right here. We'll call this receptor fibrinogen. So fibrinogen is going to start acting, that was secreted as an alpha granule, is going to attach here. This guy's also going to have fibrinogen receptor, and we're going to get another activated granule coming off of there. They'll be connected, and slowly they're going to undergo platelet aggregation through that process. There is one more thing that this releases, and that's called thromboxane. Thromboxane, just like ADP and calcium, are going to go on to turn on other inactivated platelets. The other part of blood, or of bleeding, is the clotting cascade. So this is actually what can make blood clot. So if you have a cut on your hand, what the scabs are, is just blood clotting. So we have two different pathways. I want to highlight these separately. The first pathway is called the intrinsic pathway. Now it starts with 12. Now, let me make a note here. You may be wondering, why am I not using Roman numerals? That's a valid question. First of all, Roman numerals suck. They don't make any sense. The letters are backwards sometimes. I get it, but numerical numbers are great. Okay, now that we're over that. So this is the intrinsic pathway, because we start with our first clotting factor produced by the liver is actually found inside the blood. So what happens is clotting factor 11 comes to 12, makes 11A, 9 goes to 11A, makes 9A, 10 goes to 9A, make 10A. So this part right here is all called the intrinsic pathway. Cool. Now this part over here, we call this the extrinsic pathway, because clotting factor 3 is actually found on the outside. It's an activating element. So 4 is going to come attached to 3, and that's going to make 4A. 10 is then 10, again, is going to come in 4A and make 10A. Now, here's where we hit what's called the common pathway, but we'll touch on that in a second. This is called the extrinsic pathway. Now we're going to have 10A plus 5, and then we're going to have prothrombin, and that's going to be converted to thrombin by this complex up here. Then thrombin is going to go on to convert fibrinogen to fibrin. Fibrin is the final step in the common pathway, which is the pathway shared by both. And then when we're done with fibrin, say we've successfully clotted up our wound and we don't need the fibrin, but we were still producing it because this cascade was going on down the line, we actually have another element in our blood called plasminogen. Plasminogen is a zymogen of plasmin, which is converted to plasmin by TPA. Activity TPA increases as we get more fibrin, just as a sort of a negative feedback loop for fibrin amounts in our blood. Plasmin loves to break down fibrin, hence why we have our hungry guy back, but this time it's not bacteria, this time it's plasmin is eating fibrin and breaking it down, so we don't have any more fibrin in our blood. That's pretty much everything.